We will continue with reaction kinetics, and we will talk about molecularity of a reaction. Okay, this is where we stopped last time, right? We discussed the order of reaction. Now let's talk about the molecularity of a reaction. Now, what is molecularity of a reaction? Molecularity of a reaction basically means the number of collisions of, so basically molecularity is the collision of number of molecules occurring simultaneously to bring about a chemical reaction. So molecularity of a reaction is basically that as many reactant molecules you have, right, they should collide simultaneously to bring about a chemical reaction. So it is basically collision of number of molecules simultaneously to bring about a chemical reaction, right? That is called molecularity. How is it different from order? We're just going to do that, but molecularity can be it can be unimolecular, it can be bimolecular, it can reaction can be trimolecular. You can never have zero molecularity because that means that you have no reactant particles, right? So in order to bring about a chemical reaction, the molecules of the reactant must what? Collide simultaneously. If you have just one species, for example, in a reaction of decomposition, right? In decomposition, we have no more reactants except the species which needs to be decomposed, right? So the species which needs decomposition is going to be the reactant. For example, ammonium. Okay, so for example, this right here. So if you see here, you have just one molecule right here, and that needs to be decomposed, right? This type of a reaction is called a unimolecular reaction. This is called what? Unimolecular, because you just have one molecule involved in the reaction. You can have a bimolecular reaction. A bimolecular would be something like 2 moles of HI giving H2 plus I2. Do you see that 2 moles of hydrogen iodide are required to make what? Hydrogen and iodine. So this right here is a bimolecular. We're not talking about the order here. We're just talking about the molecularity of a reaction, which depends on how many reactant particles or species or molecules do we have in a reaction. You can have a trimolecular reaction, which could be a reaction, for example, NO plus O2 giving 2NO2. Do you see you have 2 moles of NO and 1 mole of O2? That makes it a trimolecular reaction. You cannot have a you cannot have zero molecularity, because that would imply that you have no reactants, right? And it cannot go beyond trimolecular. You cannot have 4 molecules, 5 molecules, 6 molecules, because I mean, you can have such reactions where the overall equation may seem like you have more than 3 molecules in the reactants as reactants, but those reactions will occur then in steps. Those reactions will not occur in a single step, but they will occur in multiple steps. So it does not necessarily, molecularity does not go beyond trimolecular. And why is that? Because we need them to collide, right? We need them to collide simultaneously. And you know that in collisions, firstly, successful collisions will depend on 2 things. Firstly, all molecules must have energy greater or equal to activation energy, and the arrangement of the particles should be such, the way that they collide, there has to be a specific way as they collide, which would give us successful collisions. So the nature of collision, or I can say the angle or the direction of collision, that also matters, right? The way they collide, that's also important, because other than, if they don't collide in the right manner, there will be no successful collisions. And when you have molecules more than 3 as reactants, it becomes very difficult to have all of them collide properly or successfully. That's why we do not have reactions which have molecularity greater than 3. If you have molecularity greater than 3, then such reactions must occur in multiple steps, right? They must occur in multiple steps. Now, in multiple steps, we have the slow step and the fast step, right? And you know that if you have multiple steps, then the slowest step is what we call the rate determining step. It is the rate determining step. And this rate determining step will determine what? It will determine the rate, or I can say the rate equation. The rate determining step will determine the rate equation. And what is the rate equation? It is basically telling us how the reactants are affecting the rate, right? And how do you deduce the rate equation through the rate determining step? Firstly, if you have two-step reaction, for example, let's take an example of this reaction right here. Step 1 is H2O2 plus iodide ion giving H2O plus IO. This I'm telling you is the slow step. And then you have step number 2. That will be the fast step, which is H2O2 plus IO and H2O plus I minus plus O2. Right? So you know that this guy will be the rate determining step. And from the rate determining step, we figure out the rate equation. And how do we do that? You look at the rate determining step, and the reactants in the rate determining step will give us the rate equation. The rate equation, or the rate, will directly be proportional to what? H2O2 and I minus, right? So your rate will directly be proportional to this. And if you had any moles here, let's suppose we had 2 moles here. Let's suppose we had 2 H2O2. Then this would be raised to the power 2. This 2 is what we call the order. This is what we call the order of the reaction. Order kya hota hai? Order is basically to what power that reactant is raised to in the rate equation. The concentration is raised to in the rate equation, and that basically corresponds to the stoichiometric coefficient in the rate determining step, or the slow step, right? You never figure out the rate equation from the overall reaction. It is always from the slow step. This becomes your rate determining step, and this will determine the rate equation. What, however, will be the overall reaction? The overall reaction would be, you just add both these equations, and that would give you what? 2H2O2 giving 2H2O plus O2. Do you see that iodine right here is not even in the, because ये cancel हो जाता है ना, यहाँ से ये cancel हो गया, ये cancel हो गया. Do you see it's not even part of the overall equation, but it's still part of the rate equation. Iodide ion right here was being used as a catalyst. It was being used as a catalyst, right? So this is part of the rate equation, and it is not necessary that it should be present in the overall equation. Do you see it's not in the overall equation, but it's still part of the rate equation, right? It affects the rate. And IO right here, this is being formed in the reaction and is being used up in the reaction. IO would be an example of what? It would be an example of an intermediate. It would be an example of what? An intermediate, which is formed, used, but has no effect whatsoever on the rate, right? So the difference between molecularity and order is always going to be what? Experimental. Order is an experimental value, right? Whereas molecularity is a theoretical value. It is a theoretical value. This right here is theoretical, and order is what? It is experimental, right? Now, order can be 0. Order of a reaction can be equal to 0, but molecularity can never be 0. It cannot be 0, because this would imply that you have no reactants, right? And if you have no reactants, there is no reaction. Usually, in most cases, molecularity is equal to the order of the slowest step. So molecularity and order is usually in sync for most reactions. But there's a slight difference. This guy is a theoretical value, whereas order is a experimental value. Order can be a fraction, order can be zero. Molecularity can never be zero. It can either be a unimolecular or a trimolecular reaction, right? Now, we figured out in the previous class as to how we determine the rate, right? It is by the change in concentration, and the change in concentration could be of the reactants, or the decrease in concentration of the reactants, or increase in concentration of the products, right? And when we were talking about reactants, since their initial concentration will obviously be greater than the final concentration, the change in concentration is always denoted with a negative sign, right? Because rate can never be negative. So since the delta R or the delta change in concentration would be negative, that's why we always put it with a negative sign, right? We've done that in the previous class. Now, if you remember, there was something called instantaneous rate. What was instantaneous rate? It was the rate that you calculated at a specific instant, right? For example, if you were to calculate rate at t is equals to 0, so what would you do? You would basically make a tangent at that specific value of time, and you would figure out the gradient of that line, and you would get the rate, right? So instantaneous rate was basically the rate at a specific time. And how did you calculate that? You could calculate that by drawing a tangent at that point, and then you would take two values before that value and two values ahead of that value, and then you would get the gradient, right? Now, another way, sometimes this becomes too cumbersome and this becomes very difficult to calculate. So what you can do is you can use an integrated rate equation. You can do what? You can use an integrated rate equation, and this integrated rate equation can help you figure out the instantaneous rate without making a tangent, right? So you can calculate the instantaneous rate without making the tangent. Now, this integrated rate equation basically comes from the differential rate equation. The differential rate equation was basically the normal one, y2 minus y1 upon the normal, like if you had 2 points and you had to figure out the rate. So basically that was your differential rate equation. I'll just go back to what we have done earlier just to remind you what instantaneous rate equation was, or what instantaneous rate was. This was this, right? So this, remember, if you were to find it at 400 time, right, 400 seconds, then you had to make what? A tangent at 400 seconds, take two values before 400, two values after 400, and you could calculate the gradient of the tangent, right? Now, this was your instantaneous rate. And what was your differential rate? That was basically your average rate, change in concentration upon change in time, right? That was your average rate. Now, what is integrated rate equation? Integrated rate equation is basically a way you can calculate the instantaneous rate without having to make a tangent. You can just integrate. What are you doing here? You are integrating the differential or the average rate equation, right? By just integrating the average or differential rate equation, you can figure out the integrated rate equation, and that can give you the instantaneous rate. Now, this integrated rate equation, it varies for each order. It will vary for zero order reactions, first order reactions. So it varies for each order, and we will see how we get to these, right? It is different for different orders. Let's see the integrated rate equation for zero order reactions. What is integrated rate equation? It is basically you are integrating a differential or an average rate equation, right? So you have reactants which are making the products, right? We're just talking about the concentration. We're talking about concentration, change in concentration of reactants, right? That's how we're figuring out our rate. So you know, when you'd have to do that, you always put a negative sign because our rate can never be negative, right? So अगर आप reactant की concentration ले रहे हो, तो reactant का initial concentration will be greater, right? And final concentration will be less. So you'll get a negative value for delta you'll get a negative value for that. So that's why you put a negative sign here, just to get what? Just to get a positive value, right? So change in concentration of reactant upon change in time, right? That is basically how you calculate your rate. And we're talking about what? We're talking about zero order reaction. What do you understand by zero order? Zero order means that rate is equal to K and the reactant is raised to the power 0. So can I put this instead of this, right? So can I say it will be minus D change in concentration upon delta T is equals to K R to the power 0, because I'm trying to find the integrated rate equation for which type of reactions? Zero order reactions. In zero order क्या होता है? Rate is equals to K, the reactant is raised to the power 0, right? Now you know anything raised to the power 0 will be what? 1. So can I say it's minus the change in concentration upon change in time is equals to K times 1. Anything raised to the power 0 is 1, right? Now, if I further simplify this, it would be what? It would be, I'm taking the negative sign, this negative sign on the other side. So this will be change in concentration of the reactant is equals to minus K dt, right? Where K is your rate constant. Or now I'm going to do what? I'm going to integrate both sides, this side and this side. By that I mean I'm going to get rid of the D, right? So I'm integrating both sides, because what am I trying to find? The integrated rate equation. So integrate both sides. And when you do that, what do you get? You get reactant concentration is equals to minus KT, because you're integrating, plus I. What is this I? I is the integration constant. What is this? This is the integration constant, right? Now this guy must have a value. So how do we figure out the value of I? Okay, so far so good. I'm going to repeat. You know, reactant is becoming product. Okay, you know, rate. I'm trying to figure out the rate by change in concentration of the reactant. And if I'm using the reactant concentration, I should always incorporate a negative sign so as to prevent the rate being negative, because rate cannot be negative. So it will be minus change in concentration of reactant upon delta T or dt. And you know, rate, since I'm talking about zero order, because I want to find the integrated rate equation for zero order reactions. And what do you understand by zero order? K R raised to the power 0. So I can put that instead of rate. So I get this equation right here, and then I solve, integrate on both sides, and I get this, right? Where I is my integration constant. Now I need to figure out the value of I. So, so by now we have done what? Concentration of the reactant minus K T plus I. Okay? Ab, let's say that our time was 0. Let's talk about this. This is time and this is concentration. Okay? At T0, let me say my reactant concentration was R0. Okay? So at T0, my reactant concentration is what? R naught or R0. Okay? So what am I going to do now? I'm going to substitute this in this equation right here. So can I say it will basically be R naught is equals to minus KT plus I, right? Because R naught is my reactant concentration at T0 is what? R naught. Do you see I'm talking about instantaneous rate here, right? At a specific time. Okay. Now you know time kya hai? 0. So you know R naught is equals to minus K times 0, because time is 0, plus I. K times 0 is 0. So can I say it will be R naught is equals to I, right? So can I say the value of I, or my integration constant, would be equal to, I will be equal to what? The initial concentration of the reactant, right? And this will happen only for what? It will happen for zero order reactions. Okay. Now, okay, so this is done. Now, what was our equation? It was R is equals to the previous one, this one. R is equals to minus KT plus I. What is I? I is R naught, or the initial concentration. So I will say R is equals to minus KT plus R naught, right? Because I is equal to the initial concentration, or the concentration at T0, which is R0. Do you see this resembles what? This resembles Y is equals to mx plus C, where m, or the gradient, will be a negative slope, obviously, because it will be a downward curve. So this right here is Y is equals to mx plus C, where your y-intercept would be R naught, right? And it will have a downward slope. That is why we have a negative slope. You have a minus K, that is your gradient, right? And over here you have the concentration, and over here you have time, right? So this basically is how you figure out the instantaneous rate without having to make a tangent. You can just use this equation to figure out the the instantaneous rate. This is called the integrated rate equation, because do you see you integrated the rate equation, right? I can further simplify it. How? I can bring all the r's together, so it can go as r r naught minus r is equals to kt, right? This equation, I can further simplify it, and this can be what? R naught minus R upon T is equals to K. So my rate constant can be figured out or calculated through this, where your R naught is your basically the y-intercept, right? So this is for zero order. This is for zero order reactions, or the integrated rate equation for zero order reactions. Now, what are zero order reactions? Where the concentration of the reactant does not affect the rate. So it does not depend on the concentration of the reactant. What type of reactions are zero order reactions? Mostly enzyme catalyzed reactions are zero order reactions, because the enzyme is basically causing the reaction to take place, and the rate is depending on the enzyme and not the reactant. So mostly enzyme catalyzed reactions are what? Zero order reactions. Other than this, you have reactions on metal surfaces. Reactions on metal surfaces are also zero order reaction, because the amount of metal surface is basically that will depend the rate. That's what the rate will depend on, right? For example, if you have dissociation of ammonia, let's take an example of ammonia dissociating 2 moles of ammonia gas, dissociating into nitrogen plus 3 moles of hydrogen. This happens in the presence of platinum catalyst, which is a metal, happens at 1130 Kelvin temperature and very high pressure, right? So since this reaction is happening on a metal surface, no matter how much ammonia you have, it will not really affect your rate. The limiting reagent or the limiting factor here is your metal surface, right? So it is irrespective, like to the concentration, the rate does not depend. It's no matter what you keep on adding more ammonia, there will be no change in rate, because it depends on the metal surface. Just like that, another example could be decomposition of decomposition of hydrogen iodide. This happens on a metal surface as well, which is gold. So this will also, again, gold will be your limiting reagent, and that will determine your rate, not your reactant. Okay, no matter how much reactant you have, it will not affect the rate. The rate will be affected by how much gold you have or how much platinum you have. So the reactions on metal surfaces and enzyme catalyzed reactions, they basically are zero order reactions. Now we'll move on to the first order reactions. One second.